Question that is often asked in the context of moments concerns a person climbing a ladder. To do an experiment with a real person on a real ladder could obviously have safety implications. So I'm going to use a metre rule to represent the ladder, and I'm using a 200 gram mass to represent the person. In this position the person is fairly close to the bottom of the ladder, and in this position the person is much nearer to the top of the ladder. So with the person at the bottom of the ladder, or near the bottom of the ladder, I can slide the ladder out, and you can see that as I do so the ladder remains in equilibrium and everything is okay. If I go a bit further, we're still okay, and we're still okay there and there, but then the ladder begins to slide. So somewhere around here the ladder is on the point of sliding. Now if I were to put the person higher up the ladder, let's repeat the experiment, and you can see that the ladder only remains in equilibrium when it is at quite a steep angle to the horizontal. So I've got the ladder where it's on the point of sliding, and I'm going to use my inclinometer to measure the angle between the ladder and the horizontal, and that gives me an angle of 52 degrees. The diagram shows the forces acting on the ladder. Friction force and a normal reaction at the base of the ladder, what I've called capital Mg, which would be the weight of the 200 gram mass, and little mg, which would be the weight of the ladder, which has a mass of 100 grams. At the wall I've only included a horizontal force S, as I'm assuming that the wall is smooth. I can make some quick statements. Because the horizontal forces must be in equilibrium, F must balance S, so we have F equals S, and because the vertical forces must balance, R must equal the sum of the two weights. Now I'm going to take moments about the bottom of the ladder. Because F and R both pass through that point, they will have a zero moment. The force S will have an anti-clockwise moment, and that moment will be S times this distance here, which is the length of the ladder, times sine theta. The length of the ladder is 1 metre, so that is just 1 sine theta. Mg will have a moment that will be given by the size of the force times the perpendicular distance. That will be Mg times, and I'm going to call that x cos theta, where x is the distance up the ladder. And then the weight of the ladder will have a force of Mg. It is halfway up the ladder, so the distance from here to here is 0.5, and the perpendicular distance will be 0.5 cos theta. Rearranging this, I can write that S equals G capital Mx plus 0.5 little m divided by tan theta. Because S is equal to F, I could replace the S by F. When the ladder is on the point of sliding, we will have that F is equal to mu r. Using our expressions for F and for R, I can show that this gives mu equals mx plus 0.5 m divided by tan theta times m plus m. Now in our first case, when the person is towards the bottom of the ladder, we will have mu equals 0.2, which is the mass of the person, times 0.3, which is their distance up the ladder, plus 0.5 times 0.1, which is the mass of the ladder, divided by tan 52, which is the angle that we measured, times the sum of the two masses, which will be 0.3. And if I work that out, I get a value of 0.29. I had this expression for mu, and I can rearrange that so that tan theta is the subject as mx plus 0.5 m all divided by mu m plus m. Now I'm going to consider the person at the top of the ladder, so the capital M will still be 0.2. Because the person is now at the higher position, x will be 0.7, 0.5 will stay the same, times the mass of the ruler 0.1, divided by mu, which we calculated to be 0.29, times the sum of the two masses, which is 0.3. And solving that gives me a value for theta of 65 degrees. So my prediction is that the ladder will be at 65 degrees to the horizontal when the ladder is on the point of slipping with the person in the higher position. So let's just find out where that position is. Just sliding there. Okay, with the ladder on the point of sliding, I can put my inclinometer on there and see that I'm getting an angle of 68 degrees, which is not far from my prediction of 65. You might be interested to know that the health and safety regulations recommend that the angle between a ladder and the horizontal for safe use should be 75 degrees.